Okay, guys, so we're going to talk a little bit more about molar enthalpies of different reactions. We talked about molar enthalpy of combustion, but we're going to talk more about other reactions today. Okay? All right, so we talked, first one that we did the example with last time was molar enthalpy of solution. And just because I know that this will be confusing for some people, remember that a solution is made out of a solute, which is the amount in smaller quantities, and then a solvent, which is the amount in larger quantities, and usually the solvent is water. Okay? So when you have a solution, when you dissolve a solid into water, you not always, but you can have energy being released, and that's when the solution feels warm. Or you can have energy being absorbed, and that's actually when the solution feels cold. So like an ice pack, a crack pack, okay? So that's going to be releasing or absorbing energy when that solution is forming, okay? So the molar enthalpy of solution, and I mentioned this in the when we were doing the example, but here it is again, is going to be the energy released or the energy absorbed per mole of the solute, not per mole of the solvent. Now this is sometimes confusing because we measure the temperature change of the solution, but then we are only getting the moles of the solute itself. Okay? So molar enthalpy of solution, you would change the little x for the molar enthalpy and put SOLN for solution, and it's measured in kilojoules per mole. Okay? All right. So if heat is released, right, if it warms up, that's considered an exothermic reaction, and because you are going to be releasing what was chemical stored energy in your solid, as it dissolves, delta H is going to be negative, right? Because the energy change is going down. Oh, sorry, my animals are making noise. Okay, so if heat is absorbed, if it feels cold to the touch, that's because you have the temperature decreasing. And essentially what's happening is, remember, cold isn't a thing. You can have heat either leaving or heat coming in. Okay, in this case, it feels cold because it's taking the heat from the environment, because our dissolved molecules actually require energy to dissolve. And because you have energy entering the system, delta H would be positive. Okay, so the enthalpy of the solution, like it says, is they're determined by scientists in a lab, and we generally have a list of amounts. We can also use experimental data ourselves to determine this kind of stuff. Okay? All right. So we have to assume a couple of things when we are making a solution. Okay, so one of the assumptions that I have there is that the solvent and the solute are the only things that are being mixed. Okay, so that the solvent is pure and the solute is also pure. Now the issue sometimes is in a lab, we always try to use distilled or deionized water to make sure it's pure water. If you use tap water, it's no longer pure water anymore. Okay? Now when you are making the mass for the solution, and this is what I had talked about in the last class, you have to mix the mass, you have to add the mass of the solute to the mass of the solvent, because that's actually what's happening. And it's the solution itself that's changing temperature, so you measure the Q, the heat, in the solution. Okay? All right. So let's look at a second example, because the first example was actually the one that we did last class. So this one is now saying, in an experiment, you had 1.2 grams of sodium hydroxide being dissolved in 100 milliliters. Now I can just do milliliters to grams because the density of water is 1 gram per milliliter. Okay? You cannot do that with anything besides water. Okay? If I give you the density, because you need to use the density to get from your volume to grams. Okay, but for water it's 1-to-1, so we're good. And telling you that the initial temperature is 25 degrees of the water. the solution's temperature was 27.5 degrees, so it went up. And the question is asking, well, what's the molar enthalpy of solution for sodium hydroxide? Okay, so this is one that it would actually heat up and it would actually feel warm to the touch. And it does in real life. Okay, all right, so what are we going to do? Well, you're going to list our givens. Okay, that's what we're listing. These are from the question. From the question, the mass of our solution is them added together, the two masses added together. My initial temperature, my final temperature, it went up 2.5 degrees. Okay, so from our givens, the only thing that we can solve for right away is Q. Okay, now because we're using a dilute solution, we're going to be using the specific heat capacity of water. Okay, because it's a dilute solution. If it was a highly concentrated solution, then I would have to give you the specific heat capacity of that solution. Okay, so first we're going to find Q, then we're going to find the moles that we actually used in 1.2 grams of sodium hydroxide, and then we'll have the molar enthalpy. Okay, or molar enthalpy of solution. So Q is equal to mc delta T. Our M, because it's our solution that's changing temperature, because that's the T, then we're going to be using the solution's mass. So we've added them together, given it to us in joules. Remember that heat is the negative of enthalpy, and so delta H is negative Q. So we just take that value and we stick a little negative sign in front of it. It's an exothermic reaction, which makes sense, okay? Because look, our temperature went up 2.5 degrees, which means that energy is leaving the system, and so it's exothermic. Remember, exothermic reactions feel warm. Okay, so then we have to find our moles using our molar mass of sodium hydroxide. I've already added them together, but it would be the molar mass of sodium plus the molar mass of oxygen plus the molar mass of hydrogen all put together. And then we have mass divided by molar mass gives us our number of moles. Okay, now we have to rearrange this equation to solve for molar enthalpy. Okay, so we're going to, this right here is multiplication. So we are going to get this by itself, we divide it by the number of moles. Whatever we do to this side of the equation, we've got to do to that side of the equation. And so we are going to divide this by the number of moles as well. It was given to us in joules, so we get initially our answer in joules. We usually put it into kilojoules because that's just the standard, kilojoules per mole. Okay, so it becomes negative 35.29 kilojoules per mole of change in enthalpy when we dissolve. We haven't done a chemical reaction, we've just dissolved sodium hydroxide into water. Okay? Okay. So now let's look about combustion. Okay? So molar enthalpy of combustion. Combustion is, remember, where you are reacting generally a hydrocarbon in the presence of oxygen, and you're getting carbon dioxide and water. Now combustion, here's the thing, combustion is always exothermic. Think about it. Combustion is burning. You're never going to have a cool fire. Okay, this is not Harry Potter. There is no cool blue flame. All right, a blue flame is hot blue flame. Okay, so delta H is always going to be a negative value because this is always going to be an exothermic reaction. Okay, so by definition, the heat of combustion has to be our negative delta H, which means we have to get a positive Q. Okay, all right, let's look at an example. Okay, so this is an example where we're not going to be mixing the masses. You've got to look at this example. So it says ethanol in a spirit burner, which we call alcohol burners, okay, is used to heat 200 grams of water from 20 degrees to 75 degrees Celsius. The initial mass of the burner and the ethanol was 37.35 grams. Okay, the final mass of the burner and the ethanol is 35.5 grams. Okay, we couldn't measure the ethanol on its own because it's already in the spirit burner, right? So what was the molar enthalpy of combustion for ethanol? Now in this example, I am not putting the ethanol into the water. Okay, the water is changing temperature. So we're going to be using the Q for the water, which means we're using the mass for the water, just the water because we're not adding anything to the water. So the mass of the water is going to be 200 grams, end of discussion. Okay? Now, the temperature change is due to the combustion. So what we have to assume is that all the heat transfer from the flame is going into the water. Okay? We're assuming that we're not losing it to the environment. Okay? And that's a big assumption because, as you know, this would heat up the air around the flame as well. But to make our calculations easier, we're assuming that all of the heat from the combustion is going into heating up the water. Okay? All right. So, first we have to calculate the moles of the fuel used, which we can do with easy subtraction. Then we're going to calculate the energy required to change the water from its initial to its final temperature. Okay? That's going to be our Q value. And then we're going to calculate the molar enthalpy of combustion for the ethanol. And we're going to make that assumption that the heat transferred from the flame to the water didn't lose anything. Okay? So first, these are my givens. I have my molar mass, my mass of ethanol. I got that from subtracting the two values together, right? Because that essentially subtracted the mass of the actual spirit alcohol burner itself and just gave me the mass of the ethanol that was used, okay? Then I have my mass of water, 200 grams, and then I did the delta T already. Okay, it increased by 55 degrees. Okay, so first moles of ethanol, okay, because we have mass. We can find the molar mass. Then we're going to find the Q of water. We're going to use this for the delta H of water. And then we're going to use that to find the delta H of combustion. Okay? All right, so first moles of ethanol, mass over molar mass. Remember the molar mass of ethanol. You have to remember what the chemical formula for ethanol is. You have to draw it out if you're not sure. Okay? 2 C's, 1 OH group, and then I think 5 hydrogens. Okay? So you know how to do this. So you would do that. And then that's how many moles you have. Now, put that aside for a second because we're not using those moles. We're not using this math to find the delta H of water. Because the delta H of water doesn't have anything to do, there's no ethanol being mixed, okay? So it's the mass of water times the specific heat capacity times the temperature change. That gives us the Q of our heat that was, absorbed by the water, okay? Now, we have our delta H is always going to be negative Q, so all I'm going to do is stick a little negative sign. Okay, and once again, we're assuming that all the heat made by the ethanol is going into heating the water. Here's one of my cats. This is Ramses. Yes, Ramses, do you want to learn chemistry? Ramses doesn't want to learn chemistry. Ramses just wants to be fed. All right, moving on. All right, now we're going to solve for the delta H of combustion, which remember is the delta Hx. Okay, we just replaced the X with COMB. So we're going to rearrange. We want to get it on its own. So we're going to divide by N. What we do this side, we do that side. Divide by N. This is our moles. Value, boom, bam, done. Now this is given to you in joules. Okay? If you wanted to put into kilojoules, you can. If you don't want to put into kilojoules, you don't have to. Depends on what the question asks. Okay? All right, next example, neutralization. All right, so molar enthalpy of neutralization. So you have to remember what a neutralization reaction is. Okay, it's a double displacement reaction where we are going to be making an ionic compound and water from an acid and a base. Okay? Okay, so it says 100 milliliters of, oh my goodness, concentration. Okay, 100 milliliters of 0.5 mole per liter, so that's the concentration of sodium hydroxide, is reacted with 100 milliliters of 0.5 mole per liter hydrochloric acid. So you've been given volume and you've been given concentration. So you have to remember how to find moles from that. This is from grade 11. Okay? Now it says the initial temperature of both of them was 20.1 degrees Celsius, and the final temperature of the solution was 23.4 degrees Celsius, so it went up by a little bit. It's asking what is the molar enthalpy of neutralization. Okay, so remember you have to write a balanced chemical reaction. Okay, so we are going to have our sodium hydroxide and our hydrochloric acid making sodium chloride salts and water. Is this balanced? Count. We have one sodium there, we have one sodium there, hydrogen, there's two of them there, one oxygen, we're good to go. Okay? You have to check to make sure it's balanced though, because if it's not balanced, then you need to balance it before you move on. Okay, so we have our balanced chemical reaction. Now let's write our givens. Okay, now I'm putting it into liters, my volume, I'm putting it into liters because the formula for finding moles from concentration and volume require that you can cancel out the volume amounts, right? So it has to be liters here so that I can cancel it out with liters there. If you leave this as milliliters, you're going to get the wrong answer. End of discussion. Okay? And then here is my change in temperature that I worked out beforehand. Okay? So first thing we need to do is we need to find the moles of both. Okay? Then you're going to find the change of temperature of the water. Now I'm saying of the water because it was a neutralization reaction. Let me just go back to that. Okay? This is our solvent. This is our solute. Okay? And we're going to imagine that it's dissolved ions, okay, in the water. But it's the water that's going to be in the majority because you have water. These are aqueous solutions. So there's water here, water here. It's essentially the water that's changing temperature, not the ions that are contained in the water. Okay? So that's why we're going to find the Q of the water to find delta H. Then we're going to use that to find the delta H of neutralization. Okay? All right, so if you remember your concentration, it was the units of concentration are mole per liter, which means that C is equal to N over V. So if I want to rearrange that for N, I get N is equal to C times V. Okay? Even if you didn't remember the formula, the fact that I gave you the units for concentration told you what the formula was. Okay? So now I can multiply that by C times the V gives me 0.5 moles. It's the same thing for hydrochloric acid because they were balanced out in a 1-to-1 ratio. If they weren't balanced out in a 1-to-1 ratio, then these numbers wouldn't be necessarily the same. Okay? So I say here that because you have one of these, 1 mole is going to act with 1 mole, so 0.05 moles acts with 0.05 moles. That's just explaining ratios for you, which hopefully because you're in grade 12 you already know. Okay? All right. So now we find the delta H of water. Okay, so you're going to assume that you are adding these two solutions together so that the mass of water is equal to their the volume of water is equal to their two volumes added together. So it was 100 milliliters of this and 100 milliliters of that. So you put them together, that's 200 milliliters. The density of water allows us to go between, grams and milliliters. So we get 200 grams. We're using the specific heat capacity of water because we're assuming that the hydrochloric acid it's quite dilute, right? It wasn't highly concentrated. And so that gives us our joules. Remember, we end up with joules, not kilojoules at this stage. Then we can find the delta H from our making negative Q. It's an exothermic reaction. Makes sense because the temperature went up. Okay? If when you do your calculation and you get your delta H and it doesn't match, go back and do it again. Okay? Because it might mean that you've added something somewhere that you shouldn't have. And then that is our delta H. That's what we were looking for. Okay, that is the change for our neutralization. Okay, but we need it per mole. Okay, because we want the molar change. So you can pick either one of these moles. Okay, it's a 1-to-1 ratio once again. So you're going to have 1 mole of hydrochloric acid reacting with 1 mole of sodium hydroxide to produce 1 mole of water, 1 mole of sodium chloride. Okay, so it's all a 1-to-1-to-1 ratio, which means that we have 0.5 moles of everything. because that was what we got from our concentrations. We rearranged to get delta Hx. I've changed the x to neutralization, and there you go. And I put it in kilojoules per mole at this point because that's just the norm. All right, example 5, which is going to be our last example, okay? Molar enthalpy of precipitation. Okay, so remember, precipitate is a solid that is formed from two aqueous solutions going together. Okay, so we have 0.5 milliliters of 0.2 mole per liter of lead-2 nitrate solution at 19.6 degrees Celsius, and we're going to add that to 30 milliliters of solution containing excess potassium iodide. Okay, I could make this a limiting reactant question, but I'm not going to. Okay, so we already know which one's in excess. Okay, it's also at the same temperature, and then we're going to get lead-2 iodide precipitate at a temperature of 22.2 degrees Celsius. Okay, so the question is calculate the molar enthalpy of the precipitate. Okay, so of the precipitation of lead-2 iodide from this reaction. So first thing we have to do, balanced chemical equation. You have to balance it. Okay, so you have to do your little, to figure out what the formula of lead-2 nitrate is, to figure out what the formula of potassium iodide, to figure out the formula of lead-2 iodide. You got to use your crossover rule. That's why I was doing this. That's me crossing over. Okay, so after I figured that out, and believe it or not, this is sometimes where grade 12s lose marks because they don't remember how to do the stuff from grade 9, 10, 11. Okay, so you have to make sure you know how to draw out formulas from the names. You have to remember that because I'm not teaching that again. Okay, so there's my chemical equation. I've balanced it out. So I have coefficients here. Remember, no coefficient there or there means 1. All right, so now here are my givens. My volume I'm putting into liters because I was given concentration, which means that I have to use my N is equal to find out from concentration and volume, and that is my change in temperature that I've already worked out. Okay, so what do I need? I need to find the moles of lead-2 iodide, and I am going to use a molar ratio to do this. Okay, that's grade 11 stuff that hopefully you also remember. Once I find the moles of my lead-2 iodide, I'm going to get my Q of the solution to find my delta H, and then I'll have my delta H of precipitation, which is my molar enthalpy. All right. So, to find the moles, well, you can see that 1 mole of lead-2 nitrate reacts with, and I made this easy, okay? You already know that you have excess amounts of potassium iodide, okay? To make 1 mole of lead-2 iodide, and then the other, potassium nitrate, who cares, okay? So this means that because these coefficients are 1 to 1, made it super easy, the amount of moles of this is going to equal the amount of moles of that. Now, when they're not the same, that's when you have to use a molar ratio. Okay, and there was different ways to do molar ratios, and I have posted on Edmodo some molar ratio practice, okay, because some people don't remember how to do molar ratios, and sometimes that's the part of this kind of question that you get wrong because you don't remember how to do it. Okay, but for this one it was nice and easy because the moles were equal to each other, so I can use this concentration, I can use this volume to find the amount of moles. And this would be my moles of my lead-2 iodide. Okay, now I'm going to find the delta H of my solution. It's my solution, right? So I'm going to be assuming that the mass of water is going to be equal to the 2 masses that I added together. In reality, that's not true, right? Because some of the solution is going to be the ions, and some of the solution is going to actually be the mass of the precipitate. Okay? But just to make it easy, we're just going to go, okay, the mass of the solution is it all together. Just to make it easy. Okay? In reality, what you could do is you found the moles of your potassium iodide, so then you could find the mass of your potassium iodide. And after you did this 50 plus 30, you would subtract that mass. Right now, let's just deal with, pretending, okay? So I add my masses together. I use a specific heat capacity of water because water is my solvent. The solution is what changed temperature. Okay, so that's why I'm using the solution's mass. And that got me 870.27 joules. Q is the negative of delta H. And so I'm going to put my little negative sign there. That means it's exothermic, which makes sense because the temperature went up 2.6 degrees. Okay, then what I want to do is I want to find my delta Hx. Okay, now for this one, I am going to be using the moles of my lead 2 iodide. Okay, so it's going to be my value that I just calculated divided by the moles of my lead 2 iodide, which is down here, and that gives me my delta H of neutralization, and it's exothermic still. Okay, so I hope that clarified it. The biggest thing is you have to think about what's actually happening in the practice problem. Like, think about, are you mixing things? Am I just using one thing to heat another? What's happening? Because then that will tell you which mass to use for the Q equals MC delta T. That's where people run into difficulties. Okay, so just be careful with that, and I hope you guys understand this material.